It is the second part of section 8.6, Cohen SOM networks. Here we'll see some details of the Cohen SOM network. The network has a feed-forward structure with a single computation layer as shown in this picture. This is input layer, and that is the computation layer, which is the output layer. There's no hidden layers. Each neuron is fully connected to all the source nodes. So if you are choosing a neuron from the computation layer, then that neuron is connected with every node here in the computation layer. So that one node from the input layer and one node from the computation layer are selected, then the pair will be connected. Such a network is called a fully connected network. The SOM is a fully connected network having two layers, input and output only. For data type, and originally the SOM was defined for data described by numerical vectors in a subset of RD, d-dimensional space, d-dimensional Euclidean space. Now we'll deal with the data points, n data points. So it looks like discrete data sets. However, these are sample, and we may consider the behind the space of input as continuous space. So usually for the input space, we may consider it as a continuous space, and the output space as now discrete space, because it's a simple collection of units and neurons. So for SOM, it's also the same. The input space is continuous and output space is discrete. Okay. There are four major components for SOM: initialization, competition, cooperation, and adaptation. In the first step, initialization, all the connection weights are initialized with small random values. Okay, let's go back to the picture. And for the neuron, the connection is made along with connection weights, so that for each kth neuron, and we have to assign a weight, but that must be a vector, because for each node in the input layer, they must be connected, so that WK has this form, W1K and W2K, so that the last one will be WDK. Right? This weight vector for a neuron will be in the d-dimensional space. Okay. Those values are initialized with small random values. In the second step, okay, for each input point, the neurons compute their respective values of a discriminant function. Okay, that means that a discriminant function will be provided, and each neuron will compute their respective values from the discriminant function, and then among the values, the neuron having the smallest value will be declared as the winner. So in this way, the neurons will compete each other. In third step, now here, okay, and the winning neuron will determine the spatial location of topological neighborhood of excited neurons. However, it's not only the winning neuron and also the neighboring neurons will be here now cooperated and updated so that it is a kind of a smoothing the neighborhood of the winning neuron. In the final step, an adaptation is happening. That is exactly the learning. Here, we have to find, through this step, we have to find the change in weight so that earlier stage weight vector, now it becomes weight metric, and that will be updated from the earlier one plus now change in weight metric. So here that the learning is exactly the adaptation, but the winning neuron will have larger value and neighboring neurons excited will have a small change so that here the winning neuron will be more observable. Okay. Here the SOM is an unsupervised system based on competitive learning. Okay. So because of this competition, the result will be here the neurons are forced to organize themselves so that automatically some global structures will come out. Okay. Now let's go to some detail about the competitive process. The input space is d-dimensional, and the connection weights between d units, so that in input layer we have d input layer units and the kth output neuron. Now the weight vector can be defined in this way. Earlier already we considered that. Now in competitive process, we have to declare one neuron and based on a given discriminator function. Here we define discriminator function. This is an example. You can define different discriminant function. Okay. Here in this definition, we'll use the Euclidean distance between x and the weight vector, so that for given input and for kth neuron, the distance, Euclidean distance squared, is now the discriminator function. Okay. So here the distance, the discriminator function has smaller value, then the corresponding neuron will be declared as the winner. Okay. Now in cooperative process, okay, in neurobiological studies, it is found that there is a lateral interaction between a set of excited neurons. Here, one neuron is fired, then its closest neighbors tend to get excited more than those further away. So we mimic exactly the neurons, and so that we'll try to define neighborhood function for cooperation. There is a topological neighborhood that decays with distance. Okay, so we define neighborhood function. Okay, and K is the number of units in the computation layer. Then, and here at time t, so in each iteration later on, in next time, here the value will be changing, so that at a time, t's time, neighborhood function h of t is defined on k by k, and it should satisfy the following properties. It must be symmetric with the diagonal 1, and KL, HKL, the KL component of the H, and depends only on the distance here now measured between unit K and unit L. And also here the neighborhood function should decrease with increasing distances. So for those conditions, several choices are possible. However, the most popular one is Gaussian shaped function. That is defined to be now exponential minus distance squared over 2 sigma squared. Now that is a parameter, but as time increases, the sigma squared will be shrinking. That means that once it is small, then the value will decrease. Okay, h decreases with increasing distance, but if sigma becomes smaller, then the decreasing is much faster, so that cooperation is now less involved. So in this way, we can choose sigma. Okay, now go to the adaptive process. The SOM must involve a learning process, and so that the outputs should be self-organized, and also the future map between input and output must be formed. Here, this is a learning rule. Okay, and for the topographic neighborhood, the unique neuron gets its weight updated, and its neighbors will have their weights updated as well, although the magnitude is not large as the unit itself. And here, so that the weight update rule can be formulated with this change, and eta t times now h ixk, now x minus wk. For kth neuron, such update rule can be formulated. Here, I of x is the index of the unique neuron. From the comparative process, the unique neuron will be chosen, and then from that unique neuron, now h will be decided depending on the distance. For example, we can use such distance measure, and h will be decided. And then again here, learning rate must be involved. Again, this learning rate is usually decreasing during the iteration. So the effect of each weight update is to move the weight vectors of the unique neuron and is the neighbors toward the input vector. So that if it is convergent, once the computation update is done, then looks like WK is a kind of a representation of the point belong to a kth cluster, kth group of the points. So that is, because this running rule, we can interpret the result in this way. Okay. Here, the running rule, that one, has several properties. Maximal at the union neuron, because that is the largest one. And when here the k is the same as Ix, now symmetric about that neuron now, because the measure is made symmetrically. Okay. Now decreases monotonically to 0 as the distance goes to infinity. Yeah, of course here, because we are using this Gaussian-shaped function for the discriminant function, it must be satisfied. And translation invariant, in the sense that here the measure is independent of the location of the winning neuron. Only is distance dependent, right? Okay. This is end of part 2. We'll continue in the third part. Thank you.